Today's presentation is titled Accelerated Bridge Construction with Concrete Segmental Bridges. And as I was introduced, I'm Randy Cox, and I'm the manager for the American Segmental Bridge Institute. Today's outline, I'm going to discuss, provide a brief introduction to segmental bridges. Then I'm going to provide some information on precast segmental bridges that are constructed in balanced cantilever, span by span, and then I'm going to move into some substructure applications for segmental and provide some information on post-tension connections and brief you on the new PTI ASBI Grouted Post-Tensioning Specification, and then finish with a few concluding remarks. For an introduction to advantages of concrete segmental bridges, I need to talk a little bit about the structural advantages, which are redundancy. Segmental bridges are quite redundant because of the many load paths that they have that are provided by the load-carrying post-tension tendons. Each web will generally have 3 to 4 longitudinal tendons that add to the redundancy of these structures. They're also quite robust. Overload capacity is generally quite good. In most cases, the construction loads that these bridges see are greatly more so than the live loads that they will see through their life. They also are quite insensitive to fatigue. Stress ranges are quite low, so fatigue is not a concern. Concrete box girders offer great fire resistance, and that's definitely a structural advantage. They're also very stiff bridges. Deflections are generally not an issue and can be handled quite easily through the design and construction. And lastly, but not least, concrete offers great durability, and that's one of the strong advantages for segmental bridges. Through this presentation, I will introduce you to several construction techniques, but also the purpose of this presentation is to introduce you to some of the technology and terminology that's involved with segmental construction. I'm going to begin today with precast balanced cantilever construction, and my example today will be the Four Bears Bridge in North Dakota. This bridge was opened in 2005, and the total length is around 4,500 feet. The typical span lengths in this bridge are 316 feet, and the question may come up is why precast? Well, in this situation, there's seasonal construction requirements where precasting can occur year-round, and the erection of the structure in the field can happen during the summer months when the weather is in better shape. This bridge also has an integral wearing surface, and you'll hear me talk about this throughout the presentation today. Several of the bridges I will show will have this type of wearing course. And what it is there's a 2-inch additional concrete depth that's applied to each segment, and then that acts as the integral wearing surface. After the bridge is constructed, then it's ground down for rideability, and that integral wearing surface provides protection from chloride intrusion, and in the future could be removed and an overlay applied if it ever becomes problematic. This next slide is showing the precast operation from a distance, and you can see on the picture on the left, you can see the storage location. I'll get my cursor up here. You'll see the segments in storage, but also you'll see the shed behind the storage area, and that's where the segments are actually being fabricated. The picture on the right also shows more of an aerial photo, and you see the segments that are in place. The wider segments here are the typical span segments, and the narrow segments are the pier segments because they, of course, weigh more and require a lighter section for lifting. There's 482 superstructure segments in this bridge, and the casting yard is in close proximity to the end of the bridge. And as I said, there's an indoor casting facility, and we'll talk more about that. Here you see a prefabrication of the reinforcing cage. This helps expedite the casting operation. And then we have a view inside the casting barn. You'll see on the left photo, you see there's the wet cast. What we call the wet cast is the area here where you see the reinforcing, and that's where the concrete will be placed. And the match cast segment is over here on the right, and you'll hear more about this when I get into the presentation. This is a short line method of casting. So the casting machines are inside the shed where they can cast year-round and not be affected by inclement weather. This results in better quality construction. Once the segments are cast, they are positioned out into a finishing location, and over here on the right you can see a segment that's been moved out of the casting location, and the finishing takes place. It's moved on out, and then the segment lifter picks up the segments and takes them into storage. Here we see the transport of the segment from the storage area to the site, and in this site they are barging the segments out for construction. The photo on the right, something I want to point out, this project also used precast footing shells, and you can see here where my cursor is, the precast footing shells on the barge ready for installation. So those are positioned out in the lake, and then piling are driven through the template that's in the base of that footing shell, acts as a dual purpose, and then the reinforcements placed in there and then cast. The segments you see here on transport is a pier segment. Like I say, it's a relatively thin segment because of the weight. Here we see segment delivery to the working area. The segments are placed, offloaded from the land, and placed on a barge. Barges transports the segments to the location where they'll be erected. Pier table erection occurs based from a barge and a crane. The crane lifts the segments up on top of the pier. There's some supports that are used to stabilize the pier segments. The pier segments are two halves, as I mentioned, because of the hauling weights, lifting weights, etc. Those segments are then they're epoxied and then temporarily stressed together to provide a squeeze out of the epoxy. They match up to make the pier table. Here we see the erection of the segment, and it's being erected using beam and winch. There's multiple ways to do this type of construction. Beam and winch is one of the methods. So the segment is transported underneath the cantilever location. The segment's attached to the cables, and then the beam and winch lifts the segment up into position. The segments then are held apart slightly. Epoxy is applied to the joint, and then post-tensioning is applied to fit the segments up in the final position. Here we see at the end of the cantilevers, there's a typical closure joint, and the closure joint is then formed up to follow the shape of the segment. On the lower left, you will see the closure joint between the tips of the cantilever. The beams act as strong backs to facilitate the tip alignment. In some cases, the tips may not be exactly in line, so these strong backs help pull the tips together so that so they match up. The typical erection of the bridge, there was 4 to 6 segments erected per day, and that's 40 to 60 foot of bridge. The maximum segment erection was 100 feet using 10 segments in one day. The entire 316-foot span could be erected in 9 days. And this is a final photograph of the Four Bears Bridge in North Dakota. It's very aesthetic. It's on the Indian Reservation, and there's some motifs that are applied to the bridge superstructure, both on the side of the webs and also up on the railings. So for balanced cantilever erection, the segments can be erected using barge-mounted cranes, and we saw that in the previous photograph with the erection of the pier table. Ground-based cranes, of course, can be used. Beam and winch on the cantilever ends, and that was what was used on the Four Bears Bridge. Or an overhead gantry could be utilized. So there's different erection methods that can be can be used by a contractor to get the segments in place, depending on the situation they have, the specifics of the job site. Here's another balanced cantilever project. This is the new I-35W bridge in Minneapolis. It was opened in September of 2008. It's 1,214 feet long and has a 504-foot main span. The main span was constructed using precast concrete segmental. To generate those segments, or to build those segments, fabricate those segments, the long line method was used. And what you see here are the main lanes of the interstate that were closed because of the other bridge being out of service. A long line, which basically means the forming system set up for the entire span, and each segment is cast, just very similar to a short line method, but each segment is cast together, and then they're separated to create the individual segments. You can see the enclosure that allows them to work through inclement weather. That's out here in the center of the long line area. You can see the segments that are there on the left that have been cast, and then the forms on the right awaiting segment casting. And so the 120 segments were placed in 47 days for the 504-foot main span. From the notice to proceed to the close of the main span, that time period took 9 months. So very, very rapid project and expedited construction. And precast played a major role in being able to do that. Here we see the Victory Bridge over the Raton River in New Jersey. And here are the spans, or the approach spans are 150 feet, and the main navigation span is a 440-foot precast span. That is a record in North America. This bridge has an integral wearing surface that I discussed earlier. The first of the twin bridges opened 15 months after award of the project, and the second was opened 9 months later. So precasting expedited the project. This also utilizes a precast substructure, which I'll talk about in the future here. I also want to show the Route 36 Highlands Bridge in New Jersey. This bridge opened in 2010, and it's twin 1,600-foot bridges. This is a bridge which has been introduced as precast from the footing up. And the reason for precast was the short construction season. This is a tourist area, and construction had to occur in the off-tourist season, so that precasting facilitated that by allowing the precasting to occur all year round, and then the construction could occur in the non-peak periods. The reason for concrete segmental was based on durability. This bridge is in a marine environment, and the owner felt that concrete offered the best solution for durability. Now I want to move into precast span-by-span superstructure construction. This is another method for building precast segmentals. Talk about the Susquehanna River Bridge in Pennsylvania. This bridge was, notice to proceed was in November of 2004, and it was opened in May of 2007. It's twin 5,910-foot bridges, very, very rapid construction. The typical span length for this bridge is 150 feet. It also has an integral wearing surface. So what we see is, in many cases on these newer segmental bridges, especially up in the areas where de-icing chemicals are utilized, is we see the application of the integral wearing surface, which once again is an additional 2 inches of concrete on the top slab that can act as a barrier for chloride intrusion. Concrete segmental was chosen once again for durability reasons. Here we see the location of the casting yard and the bridge. The bridge is right at the end of the casting yard. You can see the storage there where the arrow points for the casting yard, and you can see the casting cells over here on the right. This was out the Penn Turnpike Commission could look out their windows and see the operation. So They were under a watchful eye during the construction of this bridge. This shows the cross section of the segment. You have an 8-foot 8-inch deep box that's about 57 feet wide, single cell. Maximum segment length was 13 feet, and the weight of those segments were approximately 104 tons. A close-up of the precasting operation. Once again here we can see the storage area. We see the pier segments, which are the thinner segments, and then the main span segments are out here. We see the transport device there on the lower right. The casting cells are up here in the sheds, once again to allow casting to occur year-round, regardless of inclement weather or not. There's some prefabrication that goes on out here. You can see the reinforcing steel and some of the tie-ups of the reinforcing cages that are occurring. This had three typical casting cells and then one specialty casting cell. One of the innovations that the contractors are always looking for is how to expedite the casting operation, and this used a unique core form that was easily extractable from the core of the box. There on the right you see the prefabricated reinforcing cage that once again helps expedite the fabrication of each segment. You heard me talk about long line casting. Well, the more common method is using the short line method, where you have what we call the wet cast segment in the forms on the right, and then the match cast segment on the left. As you see here, this wet cast segment is cast. Well, let me back up. This forming system is set. The reinforcing cage is installed, and all the appurtenances, the post-tensioning, etc., is placed in there. The match cast segment is in the position that matches the geometry of the structure, the required geometry. The wet cast segment is generally in a plumb position, and the adjustments are made to the match cast segment. There's a bond breaker that's applied to the concrete surface between the segments, and it's a simple mixture that's applied to allow the segments to separate without damage. And then the wet cast is cast. When that reaches its required strength, the wet match cast is moved into a finishing location, which is shown here on the left, where they can patch any defects that may be there, and then that segment is then put into storage. So the match cast segments roll in that position. The segment that was a wet cast segment is moved into the match cast segment. The forms are reset, and the process starts all over. Here we see the casting of the wet cast, and on the right you see the match cast. The worker here is applying the concrete into the webs. I want to point out the transverse post-tensioning. These white strips that are in this location are the transverse post-tensioning. One thing I want to point out is the durability of the deck is greatly enhanced because of the top slab. Because the top slab is post-tension in two directions, and that is one of the great advantages of segmental, because you do get the two-way post-tensioning, which greatly reduces the cracking that could occur in the future. After the segments are finished, here you see on the left, you see the segment in the finishing position. They're transported out into storage and placed for storage, and then for later transport to the job site. Here we have the segment loader picking up a segment, placing it on the transport to take to the job site. Once again, we have some photos here of the transport up on the upper left of a pier segment. We have this bridge was erected from above on a truss. What we see here on the lower photograph is the erection trusses that are underslung under the wings. We have a segment loader that's on top of the bridge. The segments, you can see the segments here in position on top of the bridge. The truck's back down. The segment loader picks the segment up, as you see in the upper right, and then moves it out into position, rotates it, and sets it on the truss and then rolls it into the forward position all the way to the end. This bridge was erected from above because of the water depth of the river was quite shallow, and it did not facilitate the use of barges. Also, there are railroad tracks on this project, and allowed the erection to occur above the railroad tracks without getting any crane locations down to disrupt the rail traffic. Here we see the segment loader rotating the segment and placing it on the underslung truss. Some more photographs of the construction. Here on the upper right, you will see the segment loader placing the last segment of the span. The segments are gapped open 4 or 5 inches, and then epoxy is applied to each segment. Then they're temporarily post-tensioned together to squeeze out the epoxy. Here we can see the application of the epoxy. The segments are gapped open. The workers apply the epoxy to the faces of the segments, and then there, like I say, there's some temporary post-tensioning, which you'll see a detail of here in a few minutes, that allow the squeeze out of the epoxy. And then at each end of the span, there's a narrow closure joint that's made. And this is on the right here. You see the workers placing the closure joints. Here we have the interior of the box, and I can show you the locations of the temporary post-tensioning. Up on the upper right up here, you see the blister that's on the inside of the box with the 2 holes. Temporary PT, usually thread bars are applied through those. Also down here on the bottom, you can see some blisters on the bottom of the hole. That allows temporary post-tensioning to be applied there. That facilitates the squeeze out of the epoxy, which you can see here, the joint of the segment. You can see some epoxy that has come out of the joint, which is good. Squeeze out is what you want to see. This also shows the layout of the permanent post-tensioning. You can see where it comes from the high point at the end of the pier, down through the deviator, and then along the bottom at mid-span, and then back up at the other end of the pier. On both sides, you can see here on 4 tendons on the left, 4 tendons on the right. Those are the main load-carrying tendons of the bridge. We also can see in this picture on the lower photograph, you can see an open duct here, which allows for future post-tensioning if necessary. So there's always provisions made for future PT in these bridges. This also, boxes facilitate carrying utilities without having them outboard or out where they can be seen, which greatly enhances the aesthetic value of these bridges. So here we have some utilities. On the upper photograph you can see, and on the lower photograph you can see the utility attachments to both the web and to the under the soffit of the bridge. Here's the post-tensioning operation at the end of the span over the pier. So these tendons go down, like I say, from the high point to the low point, and back up to the high point of that span. The post-tension ram's applied, and then the tendons are stressed up to the required load. You can see here on this side over here on the left side, there's an empty post-tension duct, and that allows for future PT. And then you can see some open holes, one with the light that's been placed in there. In this hole here, that provides for the continuity tendon for the span that has not been erected yet from where we're taking the photograph. There'll be a span there, and these tendons stitch over the support to provide continuity. The erection rate for this bridge were 3 days per span, and this shows the final photograph of the bridge. Quite an aesthetically pleasing structure. I'd like to move on with the Garçon Point Bridge. This is another bridge that used a precast superstructure and a precast substructure. It opened in May of 1999, and it's over 18,000 feet long. And the reason I want to show you this is this project still holds the record for span-by-span construction rate. 7 spans were erected in 7 days, so 980 linear feet of bridge were completed in 7 days. I also want to talk about the Selman Expressway. This is a great application for an urban environment where you have congestion, traffic congestion. This structure was placed in between the medians, and there's areas along the median that are 6 feet distance between the back of rails. So the construction was able to occur and not greatly disrupt traffic. There's no integral wearing surface on this bridge because this bridge is in the southern area in Florida, in Tampa. No need to worry about chloride intrusion. The maximum rate of erection for this structure was 2,400 linear feet in 1 month. The typical span length in this bridge is 142 feet with the maximum span range of 156 feet. Here we have some quotes from the public, and these are great. This is great input to get back from the traveling public. You can see up here the first feeling, George Jetson, for real. By the time I'm at my destination, it's been 12 minutes, suburb to city. They charge $1 for the toll. It should cost $2. So that's just an example of how the public felt about this structure when it was opened up. This is a reversible structure. So inbound into Tampa, the structure is open for all inbound traffic in the morning, and then outbound, it's reversed, and it serves as totally outbound traffic for the evening. So span-by-span erection, segments can be erected using an underslung truss. They can also be erected using an overhead gantry. Segment delivery can be from above or below. So there are certain situations where you can use a crane to lift the segments off of your transport and place them directly onto the truss, or an overhead gantry could actually pick them up and put them in position. I'll talk a little bit about precast segmental substructures. Once again, we'll talk about the Victory Bridge in New Jersey, and talked about that earlier. This bridge utilized a precast, not only superstructure, but substructure. It opened in 2005. They're almost 4,000-foot long bridges. Very similar type of construction to what we've seen with the superstructure. You can see there on the left the prefabrication of the reinforcement, and on the right you see some of the column capitals that have been they're in storage. Precast substructure construction for this project began very, very quick after the notice to proceed, 6 weeks to be. Here we see the short line casting operation. This is a short line casting operation in the vertical orientation. The segment on the bottom is the match cast. The segment on the top is the wet cast. So after this wet cast is complete, and it's met its strength, it's lifted off because there's a bond breaker once again that's applied to the interface. It's lifted up. The segment on the bottom, which is the match cast segment, is placed into storage, and then this one that was the wet cast is set down into the match cast position. The forms are repositioned, reinforcing steel, etc., are placed, concrete placed, and it just repeats itself until each pier is complete. And geometry is controlled by once again by orienting the segments to match the required geometry. Here's one of the details. There's several details that are utilized for precast piers, but this specific project used loop tendons. And what you have a footing that's in place. Then you have a tendon that's installed in the vertical position. It follows down through a loop and then back up. And there's connection details that are all depending on job to job. And this is one of the details that's been utilized. Here we can see the segment being transported into place. This is the existing footing here on the left. The segment's placed down into the pocket that's been formed up. And once it's shimmed up into position, into the correct geometry position, the segment's grouted into place. And you can see here on the left, the starter segment has been placed and grouted in position. The photograph on the right shows some of the finishing of each of the segment. You can see the sure key. You can see the ducts that will facilitate the post-tensioning. Once again, the segment joints are epoxied The workers place the epoxy on the segment joints. You can see the shear keys for each alignment keys for the pier. You can see the ducts for the post-tensioning. These bars, these thread bars, are temporary post-tensioning that allows the contractor to place the segment and then squeeze out the epoxy to achieve the correct joint thickness and geometry. Here we see the cap being placed on top of the pier. The last segment has a different detail. It has the anchorages in there for the post-tension tendons. On the right, the post-tension tendons have been installed and they're being stressed with these rams. The erection rate is rapid with precast piers. These piers, the 100-foot tall piers, were erected in 1 day. Of course, the starter segment has to be placed the day before and grouted into place, and that grout has to achieve strength before proceeding with the placement of each segment. But it's relatively quick construction, and it facilitates and expedites the job. I want to talk a little bit about precast cofferdams. On this project, on the Route 36 Highlands Bridge in New Jersey, precast cofferdams were utilized. This is the project that I spoke of earlier that was precast from the footings up. You can see over here on the far right, the forming system is in place. The center here shows the reinforcing cage being installed, and then the final section of the precast cofferdam is there ready for load out. You can see here on the left, the footing reinforcement. Now the shell's in place, is being held in place. The precast piling were driven through the bottom slab. That bottom slab acted as a template. The cylinder piles were driven through there. The reinforcing steel is then tied. Concrete is cast into that shell, and then the precast piers could start from that point up. I also want to talk about precast pier shells. This is another installation or another specialty type of construction. Precast pier shells are used. They really help reduce the hauling weights for these for the pier tables. The pier tables have heavy diaphragms, which greatly increase the weight. You saw some other earlier photographs where the pier tables were built using 2 pieces. This allows a 1-piece construction. But one of the great advantages of this type of construction, especially in the seismic region, is it allows an integral superstructure to column connection. And you can see here on the picture on the right, there's no bearings in this connection. The reinforcing steel from the column goes up into the superstructure, and it's cast into the diaphragm, allows a full moment connection. You can see here on the left, the reinforcing steel is tied into the shell, ready for casting, and what results is there on the right. I want to talk now, switch gears and talk about connections, and specifically about post-tensioning connections. And many ABC connections require post-tensioning. The Post-Tensioning Institute and the American Segmental Bridge Institute got together and formed a joint task force to develop a post-tensioning specification, and it's now available for use, version 1, and this is the founding document. This is the cover of it. The joint task group consisted of design firms, contractors, suppliers, academia, and owners. So we had all aspects, all involved to generate these specifications. We took several examples from different DOTs and took the best practices and incorporated them into the spec. So why do we need a post-tensioning specification? Well, we really felt it was necessary to create a uniform standard for the application of grouted post-tensioning. And we also have seen a lot of misapplication around the United States with contractors and with owners even that really, because post-tensioning is not always performed and it hasn't become a standard, that we really felt that it was necessary to create uniform acceptance standards for post-tensioning systems to help facilitate post-tensioning. Some of the specification highlights include The designer gets to establish the post-tensioning system protection level. There's currently 4 protection levels that are specified within the specification, where the protection level 2 is generally the bridge system that's being specified, and that incorporates an airtight system where from anchor to anchor, the system is airtight, uses permanent grout caps, plastic ducts, a grouting that's completely fills the voids. There's also quality assurance and quality control requirements within the specs for all aspects of the post-tensioning system. There's personnel qualifications that are required not only for the installer but for the grouter. And grouting operations are also covered, and I know that's something that many owners have concerns about, but the grouting is now covered within that specification. It does reference the Post-Tensioning Institute's grouting specifications for the material specifications and installation of the grouts. Personnel training, for if you have an interest or see the need for experienced personnel, Post-Tensioning Institute offers a level 1 and a level 2 bonded PT certification. Their level 1 is the basic. It's for field installation. The level 2 provides for a post-tensioning field specialist certification, and that's generally the superintendent or the foreman for the job. American Segmental Bridge Institute also offers a certified grouting technician certification. If you'd like more information about this, there's the 2 websites, the post-tensioning PTI's website and ASBI's website information. So let me go ahead and conclude. Precast concrete segmental bridges offer many advantages, and those are reduced construction time. We talked about precasting and what advantages that has, because in many cases these bridges can be erected from overhead. There's great environmental protection that can be offered through the construction techniques. Also, because for the same reason, traffic can be maintained, so traffic disruptions are much less in the urban environment, which are very important. The bridges provide very aesthetic structures. One of the other selling points of these type of bridges is that local labor and materials can be used not only for precasting segmentals, but also for cast and place segmentals. So you can hire the local labor forces, and materials such as aggregates, etc., can be purchased locally. Quality control in the precasting operations is greatly enhanced because you're in an industrialized process, generally enclosed in many cases, within sheds, work sheds, where you can work year-round and not be concerned about inclement weather. There's also, because of these structures are constructed out of a very durable material, there's minimum maintenance requirements for lower life cycle costs, and all of those points result in reduced costs for segmental bridges. And that's a brief, quick overview of segmental construction. I have time for some questions.
All right. Thank you, Randy, for a very great presentation. At this point, I'm going to turn the screen to Ben Bierman, who's going to moderate the question and answer period.
Okay, Arad, thank you very much. Randy, great presentation. Folks, we received about 20 questions just prior to the start of the webinar, and throughout the webinar, we received about a dozen. So we'll just kind of categorize them into the areas of implementation, seismic, of course, connections, tendons, and grouting is the other category. And then the last category would be layout and constructability. So we'll start off the Q&A session at the high level with the implementation category. And so, Randy, we'll just go ahead and first question will be, do you see any special challenges with implementation of these the segmental bridges from a national perspective?
The segmental bridges have been around. Of course, the implementation began in Europe in the late 40s and moved into the U.S. in the early 70s. There's been a number of segmentals that have been constructed around the United States. There's quite a bit of expertise within the contractor forces and within the consultant and the owner areas. So implementation, of course, is can always be a challenge for a startup. We have seen projects where contractors have never built a segmental, but they quickly get up to speed when they begin, and then within shortly thereafter they're up to full speed and on the learning curve, and generally don't have many problems. And these specialized work crews, superintendents are generally available and can move from project to project, and that's usually what we see happen, is that a crew will move in that has some expertise, and then they're able to train the forces and get them up to speed.
Do you see many segmental bridges being constructed or being planned to be constructed in the next 5 years?
Do I see many segmentals being constructed in the next 5 years? Certainly. We have a number of segmentals on the books at this time, in the neighborhood probably of 20 or more. There's a number of design-build contracts that are out there that you just never know until the contractor and designer come forward with a proposal. But I expect segmental to continue to move forward, and in fact, we're probably going to see more advancements and maybe some acceleration of segmental projects in the future.
Do you see the railroad industry picking these up?
Yes, in fact, transit structures are up and coming. There's been a number of structures built in the United States that handle light rail. High-speed rail is segmental construction in Europe, especially, is the mainstay for high-speed rail, and river crossings, lake crossings, and other areas where they need to have long viaducts to handle the rail. In the United States, there is a bridge across the Escambia Bay that is a heavy rail structure. It's a span-by-span bridge, so it can be utilized for heavy rail.
Great. Okay. Well, let's move out of this category and get to the category of what I call layout. You talked a little bit about this in your presentation, the maximum span lengths. How about, what are the maximum span lengths? Are they competitive, or can they be compared to steel bridges in regards to span to depth ratios? And are there limitations on the widths?
Let's start off with the last question. Are there limitations on the lift? There are segmental bridges. There was a segmental bridge that was constructed in Canada, the Prince Edward Island Bridge, and it utilized segments that weighed 7,500 tons. So that's probably one of the most extreme. The Skyway portion of the Oakland Bay Bridge that's under construction at this time, those Skyway segments weighed 800 tons. But once again, those were the reason those loads can be so great is that there was marine transport for transport on city streets and local highways. You know, we generally try to look at 100 tons or around that range, maybe even less, depending on the infrastructure that the segments have to be carried on. So it's really a job specific requirement. The other questions, what are they, Ben?
Well, what about the width? Is there a limitation on the width of the bridge with the W?
The width of the bridge, the width of a segment can be quite wide. Multi-cell segments have been used. Now for precasting, those segments can be quite heavy. So it really just would depend on the location, where the structure is going to be built. Usually when the segments become too heavy to be transported, then we're looking at multi-box structures. You saw several examples of twin boxes being constructed, and that would help facilitate the construction of these wide highways.
Randy, what about the length? Are there practical span to depth ratios or guidelines in the segmental industry?
Off the top of my head, I can't give you an exact number, but these structures, the precast, I mentioned the balanced cantilever for the Victory Bridge was 440 feet, which I believe is a U.S. record for precasting. Span by span, the optimum span lengths are probably in the range of 130 to 150 feet. We see span ranges go up to greater than that, maybe up to 180 or greater with span by span, and as short as maybe 60 or 80 feet, depending on the geometry requirements and what they have to cross. So for precasting, the upper limit is probably in the range of 450, 500 feet. Precast, for precast, but for cast in place, which we're not talking about today, cast in place segmentals can be balanced cantilever 850, 900 feet long, and then there's cable supported structures that can be even longer than that.
Great, great. Let's talk about the wearing surface. Is a composite wearing surface ever considered in the design versus a non-composite wearing surface? And are there any advantages or disadvantages from either approach?
The integral wearing surface is not considered to act in a composite manner. Even though it does, it's not counted on in the design because it's intended to be replaceable in the future. You heard me talk about several examples of integral wearing surfaces. There's also other wearing courses that can be applied that can be bare decked. There can be a bare deck with no integral wearing surface, and then the rideability is achieved by just doing some minor grinding on the surface. And then also there can be concrete overlays that could be applied, or asphaltic overlays that could be applied.
Is there a general trend from one method versus the other, bare decks versus some kind of overlay, or is it just owner specified?
It's really dependent on the location of the bridge. If you're in an area where there's many de-icing chemicals being applied, then it's advantageous to utilize the integral wearing course, the integral wearing surface, and that allows to an additional barrier for chloride intrusion. Even though the concrete is generally going to be a high performance type of concrete, very low permeability, and that the deck is generally crack free because I talked about the two-way post-tensioning. It's still chlorides can still penetrate concrete, and the owner then could in the future, 25 or 30, 40, 50 years down in the future, could mill that surface off and then reapply a concrete overlay. So where there's areas of de-icing chemical, concrete overlays are an advantage. Rideability can be achieved quickly using asphalt overlays. So in some southern locations you see asphalt's used, and then in other locations you see bare decks, just because there's no application of de-icing chemical.
Great. You showed us bridges in seismic zone regions. And so obviously these can be applied in seismic areas. Are the bridges cost effective compared to other bridge types when seismic issues are on the table?
Yes, these bridges in many cases are bid against alternate designs, and of course low bid is the one that takes it all, so through just we see the use of segmental bridges being awarded for many of these projects. There's a lot of use of segmental bridge in seismic regions. You see on the western portions of the United States the utilization of segmental structures. There was always concern about the loads of the superstructure, the heavy superstructures. In California, there was a lightweight superstructure that was constructed, which helps you with seismic. The detail that I showed of the pier shell was a structure that was built in Washington State on the Interstate 5, where a seismic connection was necessary. So like I say, we see a lot of use of segmental bridges in seismic regions. Great.
All right, let's move on into some of the details, constructability, and we'll talk about some of these joints and post-tensioning and grouting. How can level 2 corrosion protection for grouted tendon, that's the airtight ducts, how can that be achieved with the precast segments?
Well, within each segment you have, well, let me back up. A protection level PL2 tendon requires a plastic duct, a grout cap, which is installed over the end of the tendon. It has certain requirements in there for the grouting ports, that require positive shutoffs, etc. So it's that creates the airtight system. For a precast segmental, you would have the plastic ducts which are contained within each segment, and then at the end you would have the anchor that after post-tensioning is applied, you would have a permanent grout cap that's installed. Between the segment joints, you have two things that are going for you. You have the use of the epoxy, and the ASHTO requires the epoxy to be applied to both faces of the segment and then pulled together to squeeze out for adequate joint protection. But also the ASBI, the PTI ASBI specification requires for a PL2, it requires joint couplers to be utilized between the precast joints. And those couplers are tested to ensure that they meet the requirements for the system airtight test. And they're required to be able to hold 150 psi pressure test and not leak air.
Okay. Let's talk about the joints between the segments. The epoxy. Who makes it? What's the working time? Is there any strength requirements with epoxy or performance requirements?
Talking about epoxies, there's several manufacturers of epoxies, and I really don't want to go into specific names, but it's readily available through suppliers, through construction suppliers. The epoxy does gain strength, and there are requirements for the material to be provided. However, it's not counted on within the design. The epoxy serves two purposes. It serves the purpose of lubricating the segment joints. You saw the pictures of the shear keys. So you have shear keys at the joint, and when those segments are pulled together, the epoxy lubricates those areas and prevents spalling from occurring during the fit up. It also serves as a watertight joint, and Texas DOT demonstrated through their inspections. They've looked at over 20 miles of bridge and saw no leakage of their segment joints because of their standard practice of using two-faced epoxy.
Okay. When you're doing the, I guess, match casting, is flax soap or talc still the recommended bond-breaking material between segments?
That's usually what's used. It's a relatively low tech. It's usually a talc and soap mixture. Contractors have their own formulation. Segmental contractors who've been in business have got their favorites, but it's, like I say, it's relatively low tech, and they just mix up the talc with the soap mixture into a paste and apply that on the hardened concrete, and that acts as the bond breaker.
Okay. Well, what about the tendons? Is there any grout recommendations with the type of grout material you put in the tendons themselves?
The grout recommendations, and if you go back to the PTI ASBI specification, the grout recommendations are for engineered grouts to be utilized, and those grouts are not the old grouts of the past, maybe pre-2000. Those grouts were just cement and water. The new grouts are thixotropic in nature. In other words, they're gelling. They create a gel when they're not being agitated, so that they are more stable. They also utilize admixtures to densify the grouts and to provide a great, very, very thorough corrosion protection system.
The tendons themselves, unbonded versus bonded, pros and cons?
The main load tendons that you saw in the precast, the span by span, those external tendons that we saw within the box are considered to be unbonded tendons, and that's the standard construction methodology that's used. And then for balanced cantilever, there are internal tendons that are within the section in the cantilever, and then sometimes that are utilized within the slab of the bottom to create continuity. There are some advantages, structural advantages for using bonded tendons, but that's really a design criteria or designer's choice. And the bonded tendon has more ultimate moment capacity than an unbonded tendon. but that's not saying that that there should be any concerns about either choice. It's really a designer's choice.
And what about, I guess, the internal tendons versus external tendons? Do you see folks going towards the external, given the ability for inspections, or are folks going the other route and keeping them internal? And what do you see from your perspective, from the owners?
It once again, it depends on the construction technique. In a balanced cantilever, you need those tendons in the top slab during the cantilever construction. So those are internal tendons, and we need that because we need the eccentricity to provide that the necessary forces to resist the loads. In span by span, the type of construction just facilitates the use of external tendons for the main load tendons. And those do offer some advantages. They do offer the advantage of inspectability. At least you can get up and see the majority of the length of the tendon. But it really the choice of internal versus external depends on the construction method, and that's really what it's about. There are no techniques currently to know what's happening inside of a tendon. That's not necessarily a bad thing, but some owners have heartburn over that idea that they truly can't understand what's happening. But during the inspection process, there are signs that there could be signs that there are issues that are developing. In general, those happenings are very, very rare. That during construction, good oversight really helps result in a structure that requires minimal maintenance. And it's just a really good thing to watch and make sure that the tendons are properly grouted, they're installed correctly, and that they're properly grouted. And then you can rest assured that the structure will perform throughout its life with minimal maintenance.
Randy, staying in the constructability category, is there any preference between the overhead trusses versus the underslung truss?
That's a contractor's option. Erection equipment, and if a contractor has an underslung truss that's available, then they may be more likely to use that type of erection equipment, or they may have an overhead gantry that can be used. Also, if you're working within curves, sometimes underslung trusses are difficult because then you end up supporting the structure by the wing tip, and that's in the opposite direction of what the final structure the stresses of the final structure will be subjected to. So it kind of depends on the site conditions and then the contractor familiarity and availability of equipment.
Stepping back, the exterior concrete surfaces of the structures, are they typically coated with a sealant or some type of paint or waterproofing material?
In many cases, they're left unpainted. They're left uncoated with just bare concrete. The concrete's very dense. It's generally contains pozzolanic materials, supplemental cementitious materials that create a very dense, low permeable surface. And to reduce the ongoing maintenance of the structure, unpainted may be desirable by an owner. But there are structures that have been coated to provide aesthetics, and that's an owner's choice.
Great. The tendons, how are they swap clean? When you go ahead and you squeeze one segment to the other, are the tendons swap clean as the epoxy kind of gushes out into the joint? Gushes, that's a real technical term, but as it squeezes out between the joints.
Yeah, there's swabs. There's swabs that are used by the contractor to smooth out any epoxy that might get into the joint. Now, segmental couplers are being used. There will be no intrusion of epoxy into the joint. Or some cases you may see an O-ring utilized, and that will reduce the amount of epoxy getting into the joint. But swabs are a common practice by contractors to help smooth out what causes the problem is if the epoxy drips into the duct and then hardens up, it becomes an obstruction for getting the strands in place.
Okay, great. We're just about out of time here. Arad, I don't know, do we have time for one more question?
Maybe one last question.
Okay, there was one that was just posted. Are there any problems with time-dependent deflections?
Say that again. I'm sorry, I missed that.
Do you see any problems associated with deflections, specifically time-related deflections due to the loss of pre-stress or post-tension?
No, and I would say that early in the experience with segmental bridges in Europe, and there were some deflection issues due to creep and shrinkage. There's been a lot of work that's been done in that area. There's current code provisions. The European codes are generally used to calculate time-dependent effects. Those provisions allow accurate prediction of deflection, of long-term deflection of these bridges. So no, the evidence is that we don't see a lot of issues with resetting of joints, bridge joints, bearings, rideability concerns with modern bridges. Hinges are not generally used anymore in the construction of these bridges. So the bridges that are constructed today are constructed a little differently than what we saw back in the 40 or 50 years ago. And those differences help control the deflections of these bridges under the long term.
Great. Well, that will conclude our Q&A session. Randy, thank you so much for the presentation. You did a great job answering the questions. And so I'll just turn this back over to Dr. Adarad.
All right. Thank you, Ben. Thank you, Randy, for such an interesting and a very great presentation. And again, those of you who wish to obtain a PDH credit, please send an email to the address that you see on the screen. And also, we hope to have you with us for the next month webinar, which is going to be on integral abutments for ABC bridges in Vermont. The registration will be open very early next week. So with that, I'd like to conclude this webinar. Thank you.